Okay. So for those that you haven't heard about the announcement earlier of the class, if you haven't done the chapter 4 exam, I'm extending it till today at 9 p.m. So you can do it till today at 9 p.m. But remember, please finish it 1 hour before this deadline, because usually you see you may get problem when you are getting close to the deadline. Okay. So let's last class we talk about, basically we finished with talking about physical layer. Now we're going to talk about upper layer. We're going to talk about data link layer today mainly. So let's before we start talking about that, let's talk about LAN and what is LAN. Anyone can tell me what is LAN stand for?
Local access network.
Local what?
Local area network.
Local
area.
Yeah, that's true. Local area network. So before talking about Ethernet, let's talk about this because they are basically totally related together. So a local area network, as you mentioned, it's local, right? It means like it has private ownership because it's local. So it's basically, we can consider this free from regulatory constraints of like a wide area network. Then it's short distance. Usually it's like around 1 kilometer. Not necessarily. It can be. It should be. It can be bigger. It can be smaller. Like the network that you have in your house. In my house, maximum is like 100 square meters network. So, but by average, you may consider it 1 kilometer. So it's considering the basically the size of it. It's low cost, of course. It can have high speed. So it's relatively, we can call it like error-free communication because of this it's a small size and it's usually connected by the cable. So it can be error-free communication. But we don't need really like having a complex error control mechanism when we are talking about LAN network. So it can be like, for example, machines can be constantly moving in a local area network. For example, considering my house, the network that I have here, I have my phone, smartphone, I have my iPad that's connected, I have my laptop that is, so all of them are moving around, right? So because of that, keeping track of location of computers can be a problem. So we can, for example, there are certain problems like introduced with it. For example, giving each machine a unique address can maybe solve some of the problems, but it has its own characteristics. So it also needs a medium access control protocol because we are sharing one medium, so we need a medium access control protocol. So you remember I mentioned you see a medium access control protocol or media access control protocol, they both mean the same. Okay, don't get confused when you hear either one of them. They are equally popular among people using both of them. So we talked a little bit about this, I think those earlier class and a little bit last class. We have a certain type of networks. In general, maybe you can consider two types of network communication. We have broadcast network and we have point-to-point network. In broadcast network, we talked that you basically broadcast a packet to all the systems. Basically, all the systems that are connected to our network can hear that packet. And in point-to-point, basically pairs of hosts or routers are directly connected. So we can say typically local area network or LAN are broadcast. And for example, wide area networks are mainly point-to-point because we don't broadcast to all the, considering the wide area network, we don't broadcast to all of them. But in a LAN, maybe we can say generally or typically the communication is broadcast communication. So we mentioned the LAN is the size is small, so it can be like basically a house network or a small company network, or for example, a small campus network can be basically examples of example of LAN network. Also, we talk about topologies of the network last class, if you remember. Anyone remembers some network topology?
Both.
Extended star.
It was, yeah, a star topology. We talk about like the boss topology, ring topology, a star topology. So there were some basically LAN can be basically any of those. LAN can have any of those type of architecture. So this can be a typical LAN structure. We have our system. Basically, we have our transmission medium that is shared between all the systems that are connected to that. That's why we need a medium access control. We have our network interface card, NIC. So remember that NIC stands for network interface card. And then we have our unique MAC physical address. Basically, those MAC address that we are working on, or you see behind this, I don't know, your router or behind your laptop, those are unique physical address of that particular basically device that is seated on your phone or in your laptop or your switch router. So let's talk about a little bit history of the LAN and how it started. You remember we talked about Aloha network, radio network deployed in Hawaiian Island. We talked about it last class to basically start our discussion about medium access controls. So Metcalfe and Boggs invented Ethernet, which was basically random access in wired network. Metcalfe was working on studying Aloha network for his PhD thesis. That's why he came up with a better idea. In 1973, he invented basically Ethernet. He was a like a controversial researcher. Here is a little bit. I want to show you something here. But he's Robert Metcalfe. So you can Google him, but you can read about him. Basically, he was a pioneering of one of those pioneers of the internet. So he was a little bit controversial. I think in like 1995, he mentioned that the network or internet is going to collapse, and he promised that he's going to eat his word if it didn't happen. So of course it didn't happen. In another conference, in international conference of International World Wide Web Conference, the audience asked him that he has to basically stay with what he said, eating his word. So he printed his word in a cake to eat the cake. They didn't accept. So he had to blend what he said on a paper and put it in a blender and mix it with other things and drink it. Just a funny story that he has. So in 1979, three companies, basically DEC, Intel, and Xerox, they extended basically the LAN. They come up with the Ethernet 2 standard. In 1985, we had 802.3 LAN standard, or the first like IEEE standard on that, which was 10 megabit per second, the speed. Then we keep basically making it faster and faster and faster. So I'm not going to tweet about it, you can read about it, but that's a short history of LAN. So when we talk about basically Ethernet, LAN, you remember this one? We were talking about OSI layer, OC or OSI or whatever you call it. Yep. This was basically the bottom three layers. We had a physical layer, data link layer, network layer. So data link layer is basically sitting between network layer and physical layer. So it transfers data from network layer of one machine to network layer of another machine. Basically getting the, this packets here, transferring all the way to this layer. And it converts raw bits stream of the physical layer into group of frames. When you get the basically raw bits of stream of bits, it turns it to the frame. So this is just for you to remember where it was sitting, data link layer. So data link layer itself is basically consists of two parts that we talk about. Is the first part is medium access control, the bottom half of it, and the upper half, or the one that's closer to the network layer, is the link layer control. Sorry, it's a logical link control for 802.2. So remember, so data link layer consists of two different sub layers. So we refer to them as the sub layers. So MAC is the MAC, the one that we talk, different basically protocols that we have in the MAC, and for the logical link control also we have certain options. So let's so remember these two sub layers because it might be questioned later. So medium access control sub layers is basically responsible for coordinating access to the medium. It's a connectionless frame transfer service. So these are the functionalities of medium access layer control, that medium access control sub-layers that we discussed last time. But logical link control sub-layer is basically sitting between network layer and MAC layer, and it controls frame synchronization mainly. And it does the flow control. So it basically does, it manages or ensures integrity of data transmission. You can consider it managing and ensuring of the integrity of data is responsibilities of logical link control sublayer, which both MAC and LLC are belonging to data link layer. So today I'm decided to go faster because the first time we sit, it took a lot of time for basically classes. I think it becomes very boring then, that's way. This is the one just for you to remember. The last time we talked about CSMA collision detections. We talk about the back of operations, how it works. So I'm not going to go to the detail of this. So we talk about the collision detections and how it works, and we talk about basically the, like for example, you remember the length of the packet, the requirement for the packet length, how long it should be in order for us, in order for the end systems to detect the collision before sending the next frame, let's say. So I'm not basically talking about this. These are the same thing. Let's start from here because those are already, you have seen them already. You can study by yourself. So this is basically the encapsulation of the MAC frames. You remember when we were talking about encapsulation, is basically exactly like the example that we mentioned, is like putting a envelope, putting a letter in an envelope. That's basically encapsulate that envelope. So here you see the packets. Basically, you can consider this a network layer. This is the data link layer. If I make it 10, this is the, oh, sorry. This is the, why it doesn't draw. This is the network layer, okay? And this is the data link layer, both of them. So you remember that's the encapsulation. So basically we have IP packet in the network layer. When it comes to data link layer, it gets first LLC headers in LLC basically sublayer. And then that basically the whole packet now will be encapsulated in the MAC sublayer. It gets MAC headers and other headers. So this is the LLC PDU packet data unit structures. So we have a destination. This SAP is a service access point. We have destination service access point address. Service access points are basically, they identify labels for network endpoints. We can say like that in a considering OC network or C layers. They identify the network endpoint. So basically this packet should go for which network endpoint. So it's basically a conceptual location at which the OSI layers can request a service of another OSI layer. So we have for LLC packet data unit, we have this one, destination SAP address, we have source SAP address, we have some control packet, and then we have the information that are encapsulated in this. Okay, so you can see here the detail of it, not so, how to say, necessary to remember all the details of how much is the size of this one, just for you to show you how basically what type of packets we have in one, for example, in LLC PDU. And this is the MAC, basically, let's say PDU. This is the structure of the MAC frame. You remember we talked about this when we were talking, we show you the preambling. This is the preambles. We have 7 bytes of them. Then we have this basically start frame delimiters that shows us basically that frame is starting from this point. We have destination address, we have source address, we have some information here in length. So I'm going to talk about like all of them a little bit more in details. So this is basically the whole part of this from here to basically end of it is the Ethernet frame. That is the minimum is like 64 byte to 150,518 bytes. Okay. So this is basically the biggest part is the information that is encapsulated here. So if we keep going, so every frame transmission begins from basically scratch. We send some preambles in order to, but why we send the preambles? Anyone can tell me what's the purpose of preamble packets? This part? Anyone remembers? No? Basically, this was the idea of preambling was to kind of synchronize the source and destinations. You remember we were talking about coding, and we were saying like Manchester coding that you have to transmit. The idea was, for example, transmitting clock separately or including the clocks with the signals. You remember those things? Basically, source and destination clock should be somehow to some extent synchronized, because each system has a different clock due to clock drift. Our system have a slightly different clock, and when we are talking about slight different, maybe even the second of our systems are synchronized to that level of second or microsecond, but we are talking about how to say the preciseness of maybe hundreds of nanoseconds. So those small clock drift matters. So source and destination need to basically synchronize with each other. The clock of each, they need to synchronize their clock. So this is basically the frame start with this start frame delimiters that you remember it was set up 1 0 1 0 1 0 and then 1 1. When you see this 1 1, basically it was defining that okay, your frame is starting from now on. From now on is basically your frame. You remember that? Anyone?
Yes.
Okay, if you had question, just stop me and ask, okay? Because you muted all the microphone, I don't hear anything. Okay.
Yeah, okay, thank you.
So this was the one basically picture that we showed you last time. That was basically, we had these preambles, 8 bytes of continuous 1 0 1 0. So it helps receivers and sender and receiver to synchronize with each other. Then we had the start frame delimiters here, that was 1 0 1 0 1 0, then 1 1, then the frame would start from that point. So destination address and source address are another part of the MAC frame. So you remember we had different types of sending message. We had, for example, broadcast message that we talk all the systems that connected to the network can hear that. We had multicast and we had unicast. Do you remember that? Broadcast, multicast, unicast?
Yes.
Yes.
So
Yes.
those were like some of the basically options to send the message. This was the unicast, multicast, broadcast. So basically here, for example, the destination address can be a multicast address. Okay, so if it's a multicast address, everyone can hear that packet. Or if it's like a specific address for one system, it will be just unicast goes to that one destination. So other system, not necessarily other system, they don't hear that packet. They hear, but they don't drop it because it's not meant for them. It's not having, I mean, the destination is another system. So remember that that's important. For broadcast, it means everyone should deal with that packet. Maybe we are getting some information that we're going to discuss why this broadcast is important. So this addressing also can be dynamic address or it can be a static address. The dynamic address is like an AppleTalk, which is an old standard. It started with Apple, but no one is using it anymore. Or like a static addressing, which is the standard that used in Ethernet that we are still using that. We're going to talk about them a little bit later. So also the destination and source address can be single address or group address. So, and also they can be local address or global address. So for example, if it's local address, it means it is addressing for somewhere inside our network, not to going out of our network. It's for internal network. Or global address, it means it's beyond our network. So for example, this global address, when we are talking about the MAC address, okay, it's basically it's like 48 bits or 6 bytes, okay? So the first 24 bits assigned to a manufacturer, and the next 24 bits assigned by the manufacturer, okay? For example, Cisco, all the, like, for example, the devices that Cisco generates, all the, let's say, network interface cards that Cisco generate start with this 24 bits. These are like octets, so they are, each one is 4 bits. They start with this, then, so basically each manufacturer has a ID fixed for that manufacturer, and then any device that they generate, basically they give it unique address by the next 24 bits. So just remember that one is important. Also, this is like an important one here is like the broadcast packets are all basically, all the bits will be set to 1. So basically you can consider it like F. Okay, so it's all on. Those are basically broadcast address aimed for all the systems that are connected to the network. Okay, this is the same thing about talking about the addressing, the structure. So as I mentioned, the first 21st bit is identifying the manufacturer of the device, and the second half of it identifying the basically the device itself. Okay, and I talk about this, so let's move on. So then we have this 2 bytes here, that is length, or sometimes some people refer to it as a type. It indicates the higher layer protocol, mostly IP, but others may be supported, such as like novel IPX and AppleTalk. Basically, what it says here is what you're going to see in the network layer. So this is basically defining the type of the network layer that you are dealing with. Okay, this is in the Mac frame. Okay, so this is basically defining what you're going to see in the upper layers. Are you going to, for example, deal with what type of network layer, what type of TCP, what type of basically layer 4 like TCP, UDP, what type it's going to be? It's going to be defined here in these 2 bytes. And the information is, of course, the information. The padding is some extra information that we add to the frame. You remember the frame should have a certain size, as we already discussed. If the frame is shorter, then not necessarily all the frames going to be 1500, for example, bytes. Some of them are shorter, but those shorter frames going to get some padding information, like basically useless set of bits in order to make the length just as long as it should be. So basically padding ensures minimum frame size, which was the 64 bytes, the minimum. That's basically the responsibility of this padding here. And this FCS is a frame check sequence. Basically, it's any type of error corrections here. It's used basically these 4 bytes used for that purpose. So basically, NIC or network interface card, this card frames with improper length or failed CRC. Okay, so we saw that in the question. This is basically purpose of this NIC. So we have different standards for physical layer. These are some. I mean, basically 10 base 5, 10 base 2, 10 base T. These are basically all, we don't really use them anymore. 10 base T. You see the medium, for example, what type of cabling is used. For example, here it's a coaxial cable, a T coaxial cable, thin coaxial cable, twisted pairs. And for example, 10 base FX is like optical fiber. So the point is here not to remembering all these details, okay, but just getting familiar with some of them. And knowing that we have different standards and each different standard basically using different type of medium. The maximum segment length can be different. The topology of the network can be different. So basically this, like for example, T coaxial cable, which was the old standard, was very troublesome T cable that passed through the ceiling or basically floor that moves, basically connect our network. So, so from here, basically we started using hops and switch from the standard 10 base T. We moved toward basically hop and switches started basically introduced in this point in our networking. So these are again some histories about evolution of the network. I'm not really spending time. I just included in the slide so you can have them, but not spending so much time describing them. So as we basically develop, as we move forward, we just keep increasing the speed. The speed gets better and better. We talk about the topologies. So you remember we have let me go to here, this one, maybe describing it better. We have two different basically devices that you may already heard. You heard already. We have hops and we have switches. Okay, so they are not totally same things. We have an Ethernet switch is a packet switch for Ethernet frames. So switches basically have more functionality than basic hops. For example, switches can buffer our frame. If, for example, the end system is busy, switch can buffer the frame in order to prevent collision and later transmit those buffered frame to our end system. And each port in the switch is isolated and build its own collision domain. Okay, so you can see, for example, here, comparing the basic hop that is connecting basically one line to another line, switch can basically provide more functionality for us. So for example, in talking about hops, just the old-fashioned hops, collision can occur if two frames arrive at the same time. But that's not the case for switch. Switch can buffer that, handle one, then move and handle another one. This is just short notes on Ethernet hops and switches. I think you're going to have practice with packet tracer this Thursday with Juan about these two types. Okay, so any questions so far?
No.
Because you're all clear?
Yes.
Okay. So let's move. So basically, the switches was basically to improve the hop concept. When we had switches, the switches learns basically destination location by remembering the port of the associated source address in a table. For example, the switches that you have in your house or I have in my house, and because not just one device is connected, it's my smart TV is connected to them, my tablet, phone, all these devices that I have connected to them. So switch learns basically the destination location by remembering the port of the associated source address. So basically, the switches keep a table of all the devices that connected to it with their physical addressing and the IP addressing. Okay. So that then the switches use that table in order to basically forward the packets to the correct destination. Okay, we're going to see this when we talk about ARP. So these are basically fast Ethernet that mostly still are in use. We have 100 base T4, 100 base T, 100 base FX, and we saw this as optical fiber, twisted pair, Cat5, and this is basically Cat3 tables for 10 base T4. Let's move on, not really important here. So basically, this can be a typical Ethernet deployment. You have different type of, basically, let's say this is a campus. Let's say it's a campus Guadalajara. So we have different buildings. Each building can have its own basically network that the systems are connected to hub. Hubs are connected to the Ethernet switch, and Ethernet switch is connected to the basically switches or routers, and that routers are connecting us to the outside servers. So this can be, for example, department A, this building, that building. So this is a typical, basically a structure of Ethernet deployment. As you can see here, it's including our end systems, hubs, switches, and of course, routers. So, but each of them can be different type of network. Okay, not necessarily can be, for example, 10 megabit, it can be, this one can be faster, this one can be slower, and so on. So talking about data link layer, let me see the time. Okay, before I go, let me first take the attendee list. I'm sorry. Then let me close this. Okay, I skipped that slide that I was showing you because I remember I already talked about point-to-point network when we mentioned about two type of communication network, broadcast point-to-point network. Anyway, you might feel I'm going a little bit fast, but I try not to talk about exactly the same thing that you're going to read in the NetaCat, because this is the same chapter you're going to see in the NetaCat, but I don't want to be exactly talking about totally same thing. Okay, so a little bit extra things, a little bit here, more detail on this topic, on that topic. It won't be exactly the same thing. So let's talk about ARP or address resolution protocols. It's this is basically not the bottom tree, this physical layer. We have a link layer. Let's see, this is link layer, network layer, and transport layer, and other layers above it. So ARP basically is a link layer functionality, or it's a stand for address resolution protocol is what we're going to talk about it. Basically, the main idea of address resolution protocol is to converting the IP address with the MAC address. So you remember when we talk about those very first class, we talk about the network and internet, that everything works with the IP address, right? Is that's the base of the internet. We send basically packet by the IP addresses. So we do everything by IP address. But we know that in your laptop or in your phone, the thing that you have is basically the network interface card that you have has a MAC address, or basically the dedicated physical address of my device. But you don't know, for example, the MAC address of my phone, but still you are able to communicate with it using the IP address, right? But when the IP address comes basically to the switch that I have in my house and my phone is connected to it, the switch should know my MAC address, should know my exact physical address in order to transmit the packet for me. So what it does, basically, it gets the packets and use this ARP in order to convert MAC address to IP address, or the other way around. MAC address to IP address, or IP address to MAC address. So it's both ways. So this is, let's talk about it. So as I mentioned, we have the internet, which is based on IP addressing. Then we have the data link protocol that have different, for example, type of network. For example, Ethernet, ATM may have different MAC addresses. So as I mentioned, all of them have different MAC addresses. So address resolution protocol, or reply address resolution protocols, performs the translation between IP address and MAC layer addresses. So let's discuss about it. Basically, what it does is get the IP address, and if you go through the basically ARP process, ARP protocol, it gives you Ethernet MAC address, which is 48 bits. And if you give it the MAC address, it can give you the IP addressing. Basically, it does this translation between MAC address and IP address. So in order to just make it more exciting, I'm going to play the same topic in a short video clip. Can you hear it?
Not really.
You cannot hear the video that I'm playing?
I think I can hear you, I think.
We hear from your microphone, but you can.
Oh, you just hear from my microphone. Okay, let me fix this. Do you hear?
No.
No.
Oh God.
On teacher, on the preferences where you stop the sharing, I think there's an arrow there that says share computer audio.
Where? It should be here, right? Or here?
I cannot see.
Okay, share computer sound. Yeah, got it.
The MAC address is a physical address.
Okay.
Yes.
Thank you for the tip. So it's a short video talking about ARP. So I think maybe this is a little bit more graphical. So just let's watch it. It's just 4 minutes. Okay?
ARP stands for Address Resolution Protocol. Now this is a protocol that is used to resolve IP addresses to MAC addresses. The MAC address is a physical address of a device. It's a globally unique number that is assigned to every network interface card.
Okay, can you hear me too?
Yes.
Yes.
Okay, so you remember we were talking this, anyone remember we were saying the first 24 bits is dedicated to the company, the factory basically, and the latter or the last 24 bits is dedicated to device itself. It's assigned by basically the company to each device.
Whenever a device needs to communicate with another device on a local area network, it needs the MAC address for that device. And devices use ARP to acquire the MAC address for that device. So as an example, let's say that computer A wants to communicate with computer B. Now, computer A already knows the IP address for computer B, but in order to communicate with computer B, it still needs its MAC address. Now, an IP address is used to locate a device on a network, and the MAC address is what identifies the actual device. So in order to find the MAC address, computer A will first look at its internal list, called an ARP cache, to see if computer B's IP address already has a matching MAC address. In fact, we can check this ourselves at a Windows command prompt by using the ARP utility and by typing ARP space -A.
Okay, let me